here. I had to PDF scan your book in the homework pages. Yes. Yes, I'm really sorry. Let me, okay, Coach Collins, I said still no books, and he said, I'm afraid not. I will continue to scan my old books.
Tell him that I said, tell him that Hansel was
Tell him what?
I said, that's unfair. It's okay. How do we find it?
I put it in there under notes on it. Go into Canvas. All right, y'all ready? Right. All right. And so we start calculus today. Yay! All right, we're going to talk about rates of change first, which is the basis of all calculus. But some of this you know. When I say rate of change, tell me what you think. Okay, so give me another word for that. A more basic, slope. We think slope, right? Rate of change. But you're right, changing over time and that kind of thing, rates of change, right? So we think slope. I'm going to, no, this is calculus. Oh, yeah, we're done with pre-calculus.
That's all I needed to know last year. You couldn't teach that.
No, so what I decided to do was as we hit stuff that you should have learned, I'm going to embed it in. Instead of spending weeks on the front end going over stuff, the stuff that you need to know cold is what I went over with you before.
Okay.
The unit circle, the trig identities, the trig functions, that kind of thing. Yeah. Did you go to today's date? Publish. Good morning. Thank you. All right, we're going to talk about first things first. AROC, so this is our average rate of change. Average rate of change, which we also know as slope. I'm writing slope in a slope. We will refer to this as AROC from this point forward. So if I say AROC, understand I'm just talking about the slope, okay? So we call it average rate of change because we look over a span of time to find how it changes on average over that span of time. That makes sense, right? Average rate of change. And so tell me, let's see, I'm going to put also known as the slope between 2 points. But in calculus, we're going to think about it just a little bit differently. Tell me how you find slope between 2 points. Rise over run, y. Give me a little bit more sophisticated way. Besides m, like what does m equal? Y'all might not have learned this notation. Y'all see that? Delta y. Delta means change in, right? So it's the change in y over the change in x, which is rise over run, because the y-axis rises, the x-axis runs.
So y2 minus y1?
Yes. And so I'm going to define this just a little bit differently. And let me show you a little graph to try to help you understand this. I don't know if it would, I mean, I can if you text me and leave it. Yeah. I record it and upload it, but if you want to be live and participate. Okay. Just let me know. Can y'all see the way you're twisted?
Yeah, I really
Okay. Let's look at a graph for just a second, and we'll just take in the old graph. Let's see. Yeah. Let's look at these 2 points. Instead of calling this xy that you are used to, if I call this x f of x, would that make sense to you? It's the same as y, right? It means you plug in that x value to find. Okay, if I want the change, you go. I'm going to look at this a little bit differently. I am going to say from this point to this point, I am going to define this distance as h. Are y'all with me so far? So the change in x here, instead of x2 minus x1, I'm going to call that what? H. Is everybody okay there? The change in x. Because the distance between the 2 points on the x-axis, I'm going to define as being h, okay? I'm going to call that h. And this is going to make sense when we get to the calculus part of it. That's why I want to define this. Okay. H is the change in x. This is because we're getting to the formal definition of something. And so yes, it is. What then would the change in y be?
Well, there would be another letter, but I'm going to go ahead and say, what would be the change? L. F of H. Ooh.
You're close.
That was a pretty good guess.
What is this point?
X2.
What? Oh, sorry. What is this point? If this is x, f of x, and this distance is h, what are the coordinates of this point? You're close. X plus h is your x coordinate. Do you all agree? Good job. All right, so x plus h is my x. What would my y then be? F of x plus h, right? Well, then that would not lead us up to our IROC formula we're fixing to get to. That's right. Okay.
So what do we do with this information?
So I'm going to use, so now tell me how I could find the difference in y based on my new defined y.
Wait, so
Does that make sense to you?
H is just an X plus.
Okay. Very conceptual, but makes sense, right? We see where we're getting these values and these things. Okay. So this is something we're used to. We're just writing the equation a little bit differently than what you're used to. So now let me ask you this. This is the rate of change between these 2 points, right? And it's averaging the rate of change. Could I find the rate of change at a specific point? So you're saying 1 point, and 1 point alone has a rate of change. You're saying you need 2. So you're try one more time. Oh, wait, I gotta spell it. Yes. Tell me to try one more time. Instantaneous. Instantaneous. Okay, so you're saying they need to be two different points. It can't just be one point. How close could I get, though? As close as I want. So, in fact, as I get closer and closer and closer together, what is happening to my H? Smaller and smaller. Do you agree with that? What actually is it getting closer and closer to? Somebody says the same. 0, right? As that distance closes in and these points get closer together, that H gets closer and closer to 0. But if you look at my equation, the problem is if I plug 0 in for H, undefined. I can't divide by 0, right? Right. So, but it can approach 0. Limit! Oh, we need a limit. You're exactly right. We need a limit. We need a limit as x approaches 0, and that.
But it can't be 0 anyways, because it wouldn't be a slope.
Well, you're going to find that we do have a slope and a tangent line. That's a whole other, that's the next chapter, but we actually do. And we call it an instantaneous rate of change. Guess what I call this? If the other's A rock, this is I rock, because I rock, you rock, we all rock. I rock. 2, there's. So, you need a brain break already? Let me finish defining I rock and I'll give you a brain break. Okay. Okay. This is the change at a given point. This does not occur over an interval. I wanted you to get there before I just told you what it was.
So basically, if it's like a regular slope, you use that first equation. If it's this, you're going to have to use the other.
Right.
So this only happens with 1 point.
Yes, yes. But what we're going to do right now to find it is we're going to plug in some values that get closer and closer and closer to 0 and see what happens. Okay, before we actually do the algebraic. All right, so we're not over an interval. We said if you want to write down, we can't divide by 0. This is kind of what we discussed. I'm just writing it off here. So if you'd like to have your notes, can't divide by 0. Therefore, H cannot equal 0. So we get really close. For example, y'all need a brain break before we do an example?
No, we'll get a brain break later.
Yeah.
Brain break is bio, dude. Honestly.
All right. Van stands on top of a cliff and drops a rock, because that's what Van does, right? You stand on top of cliffs and drop rocks. We know what's the slope. Let's see if we tell you. What's the, so you fall at, what's the rate that you fall? 16. Oh, that's right, but experiments show that a dense solid object dropped from rest to fall freely near the surface of the earth will fall y equals 16t squared. It's 16t squared plus 9.8t something, then you got your constant over there. Okay, but we're just going to use 16t. So man drops this rock, right, from the top. In the first 2 seconds, okay, so I'm already talking about you think I'm going to talk about average rate of change or instantaneous rate of change?
I think instantaneous.
Over the first 2 seconds.
It's the first one because it's
over the first 2 seconds, I'm talking about a range in time. Okay, So I'm going to talk about average. So over the first 2 seconds, what's wrong? It doesn't work?
Yeah, the one link on there is the modeling equations one.
I can do it real quick.
Yeah, don't worry about it. I was paying.
Find the average rate of the, no, let me say it different. Find the average speed over the first 2 seconds. T is time. We'll say time is in seconds, and we will say that the height is in feet. What's the average speed over the first 2 seconds?
Well, we have two.
What is speed? Speed is feet per second here. If I'm talking about a height of feet and a time of seconds, right?
So like this
Yeah.
would just be 64. 34. It'd be 4. That's gonna be 4. It'd be 16 over 2 squared.
Okay, let's look at it. We're going to do the change in y over the change in x because over the first 2 seconds, I'm talking about an A-rock situation, right? A rock situation. Because we dropped. Did the link work this time? Okay. So as I look at this, what is the change in y? Y, remember, is my feet. So I need to know what was y when time was 0 and then what was when it was 2. When it's 0, it's what? 0. And when it's 2, 2 squared is 4, so you get 64. So what is the average speed?
Well, so
632. Right. Just think about slope. 0, 0, 264.
what do we do?
Average, yes. Sorry, I should have put a T there. I didn't realize. If you had these 2 points and I said find the slope between those 2 points, what would you do? Change in y over change in x, right? Yes. Okay. The whole point in, you're fixing to. I set it up that way for you so you could see how iRock works. Okay, so this same rock I'm dropping, right? And so over the course of 2 seconds, it averages a speed of 32 feet per second. Now, that doesn't mean that as soon as he drops it, it's going 32 feet a second, right? That's the average over the course of time. Kind of like y'all were talking about your average amount of time on your phone. That doesn't mean you spend 13 hours every day. That means it could be more, it could be less, right? Same with this. So what if I asked you, what is the speed at exactly 2 seconds? In other words, if you could stop that rock or you could look at it at 2 seconds, how fast was it going at exactly 2 seconds? So this is my instantaneous rate of change. So this is iRock when t equals 2. Okay, so yes, so let's take that same iRock formula we said, or any rate of change formula, right, with the h in it. So we've got f of, and we're going to use t for x, right? So we've got t plus h minus f of t over h. Right? Let's take that same formula. But this time, we're looking, because we're talking about instantaneous at 2, we can put the 2 in here, and we can put the 2 in here. Yes? But what's the problem? My problem's coming in my h because there is no difference here. So my question is, what happens as h gets smaller and smaller and smaller? In other words, what if I let h be 0.1? Well, what I'm going to do is I'm going to plug in some values and get as close as I can and look at a pattern that's happening with the number.
Is your denominator small?
You could. Plug in, do it though. Let H be 0.1 and tell me what you get. Okay, so let H be 0.1. Use your IROC formula, which is just slope, but this time I'm only moving over. So essentially what I'm doing is I'm doing average rate of change between 2 and 2.1. I don't know, what do you get? No.
So 2 plus, if H is 0, or 0.1.
0.1. So you're doing F of 2.1 minus F of 2 over 0.1.
Oh, 2.1.
What it, no. F of 2.1. Where's your formula? Remember, we're 16t squared. We're still with that original equation. That's 16t squared because the rock is falling. Are y'all with me? When you found average rate of change, when we did average rate of change, here is the rate that it's falling, right? Or that's how I measure how fast it's falling. The speed, right? This gives me, at t times, it gives me where I am. So if I put a 1 in, that tells me 1 second in, I'm at 16 feet. Does that make sense? In fact, a lot of your physics classes, it's a negative if it's falling, right? Because it's gone down 16
You
feet.
would put a 1 in where?
For t.
No, we're
At 1 second, we're just saying, we're going back to this formula and saying, at 1 second, it has fallen 16 feet. That doesn't tell me the speed at 1 second. That tells me how far down it's gone in 1 second.
What about?
Yes, that's what we're doing. Right,
So
right.
why would, if you're saying, but what about the square?
What about it?
So if you plug in 1, would you have to 16 squared?
You do 1 squared, exponents come first, and then multiply by 2.
Wait, how did you?
That's why it wasn't
So it is
making
one. Andy was 1 square.
No. We're still on that. We're saying if we're looking at 1 second, where is my rock? You would plug 1 in for t. And then he was saying, why is it not 16 squared? We're saying you square 1 and then multiply by 16.
That's why it was 64, because I was sitting there thinking, where did you get 64?
Right. Okay. Remember, if I'm back, even if I used this formula with the h from before, whenever I did a rock, I still can. My distance apart is 2. That's my h there, right? Because we're going from 0 to 2 seconds. Are y'all following me? So it would be 2 plugged in for that h value there. Does that make sense? Starting at 0 and going to 2. But here I'm asking you, what's the instantaneous rate at 2 seconds? So how fast was it going? Not where was it? We know it was at 16 feet or whatever it was. But how fast was it going at that point? At that exact point. So we're going to get really, really close to 0 because we know we can't actually be 0 because we can't divide by 0. So if you plug this in, I'm still in my 16t squared formula or equation. Correct. So essentially I'm finding the slope between 2 and 2.1.
So you would plug that back in.
70.56 minus.
Divided by 0.1. And what do you get? Yes.
So you just plug in for both of those f of things that equation.
Okay.
That makes sense.
This one is 16 times 2.1 squared.
There you go. Now we're talking.
This one is 16 times 2. Squared. Still this same equation.
I understand now. Thank you.
Same. Right, f of x is y, so it's just y equal, and that's what we're plugging in for x, is what's in parentheses. Right. So when I say what is it when h is 0.1, I'm saying if you only make the space between the first x and the next x 0.1, what happens to your slope? Which is your speed, because it's your rate of change. Correct.
Should we plug in another one?
Okay, so we should plug in another one. What maybe should I plug
I would say
in?
0.3.
That's bigger. What are we trying to do? What are we trying to accomplish here? That's the question. There you go. We're trying to get as close to 0 as we can. So there you go. I would try. What happens if it's 0.01? Then what? Shut up. Why is it doing that? And then what happens if it's 0.001? And as we get, it's the stupid. Yeah, hook up.
We're doing it 2 more times.
We might even do it more than that. Let's see until we can pick up a pattern with the number and see, is this value getting closer? Remember my goal, what I asked you to start with. What is the speed at 2 seconds? At exactly 2 seconds in, after he drops it, 1, 2, how fast was it going?
And what's the pattern?
Right,
Do the next
right.
one. Let's do the next one. So we can...
Okay, do the next one and see what you get. Yeah, you definitely need a calculator.
Calculator. What is that even?
Isn't this fun?
No. This makes me sad.
It's not like.
I'm good. Y'all will be mad whenever I show you actually how easy it is. It's just I want you to get it conceptual. Y'all know how I am. I want you to understand the concept here.
So the F of...
Should have known.
I need a calculator.
Why don't we do this? Y'all do 0.01, y'all do 0.001, y'all do 0.0001. Oh my goodness. It's okay. Just go ahead.
No, I'm almost done.
How do I get out of this? Holy cow.
y'all everybody keep doing 0.0. You need some of those erasable pens like I have. You want to borrow one?
Tell me where you got it.
What color, man? I have green, I have blue, purple, pink, red.
What do you think? When you look at me, what color do you think? She was right. Well, no, but I was thinking that.
This is called a friction pen, and it erases whenever. So, like, if you put it really hot, it's all together.
I have some. All right, let's just see. I'm just gonna write down. Hello.
You can put it in the microwave.
Is this the eraser?
Yeah, it doesn't necessarily even have to be that. It's
It's
not an eraser, it creates friction. And the heat and the friction.
That's such chemistry right there.
Okay, yeah. Ooh, Princess is getting closer to 64. What y'all get for 0.01?
I don't know, I get 6.4.
Hold on, 0.01, I got 64.01.
Okay, if you're still working through that, and in fact, you are correct. If I took this out all the way to 1, 2, 3, 4, 1, I would actually get 64.00016. So,
I tried to square point.
Well, it never will that way, but as I approach 2, as I get closer and closer to that distance, remember what I'm doing. I'm trying to find the speed at 2. I'm trying to get the distance between the 2 points to be as close to 0 as I can get, because I know I can't actually be 0 because 0 would be undefined, right? But I can get super duper 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 close And the closer I get, the closer I see these numbers coming to what? 64. You absolutely would. This introduces us to limits. Great job. All right, so I'm going to say the instantaneous rate of change at 2 is going to be approximately 64 feet per second. Would you say that that is a good estimate? Let me stretch your brain just a smidge more. A smidgen. Could you come up with an equation that could represent instantaneous rate of change at any value?
No, but you could. You have, haven't you? Great answer.
I'm thinking of if I'm gonna, should I just jump into limits or should I show you this? I'm gonna show you because you're gonna have to do this formally. There's always like a question or two with the formal definition of a limit or the formal definition of a derivative. So the more you see it, the less intimidating it is. For any h value, in fact, could I come up with an equation for this? And the answer is yes. If I think back to that IROC formula, yes, that's whenever something drops, that tells you how many feet it's dropped based on gravity. How many feet it's dropped after t seconds.
Don't question the scientists. Don't, are you questioning Fauci?
And it was y equals 16. Yeah, like.
Fauci, Fauci.
Just want to know why it's 16.
You're talking about the original equation? Yeah, it is.
You're like trying to give me to like explain to them like the idea of it's just that.
It's that. We could derive it and we could go into, but yeah. Some things just are. They are. Let's come up with an equation for the instantaneous rate of change given any h value.
We don't have to do any of that other stuff.
Maybe. Oh, plugging in like that and approaching a value. Yeah, we'll use our calculator and we'll use a table. And that's.
I remember doing that.
Yeah. Yeah. In fact, you could have done it for this one. I didn't specify how you had to do it. If you put y equals and you put your equation and then you go second table, it'll do it for you. All right, give me the formula one more time for IROC. F of general. Yes. Minus. Now let's apply it to our 16 t squared formula. So that means F, not F, 16 t plus h squared minus f of t. Oh, yeah. Doesn't it have to do what?
Or no, exponential version, right?
No. Now, give me an equation for the instantaneous rate of change at 2 seconds. So instantaneous rate of change when t is 2 is going to be 16 t plus 2 plus h squared minus 16 2 squared. Right? Could you simplify that any? How? 64. Could I simplify it any more? Before I distribute, what do I have to do? I'm going to have to FOIL it, right? Because exponents come first. What happens if you FOIL 2 plus h, 2 plus h? 4 plus 4h plus h squared. If you FOIL 2 plus h, because the ends multiply, and then you know that this doubles. Watch what happens. This is beautiful. Watch what happens. Yeah. Remember, this is specifically for 2 and no other value, right? This is instantaneous rate of change when t is 2. Well, but we plug 2 in. So if you wanted it for 3, you'd have to plug a 3 in for 2. All right, distribute. 64 plus 64h plus, plus 16h squared minus 64 over h. What in the world is happening? The 64s cancel out. What else is happening? Yes, Noah, yes. Say it again.
Did I not say that?
You did, but you couldn't do it in the order you said it. You had to, you said too early. Because there were values without h's on them. Like I couldn't have canceled the h out at this step because the 64 didn't have an h, and you didn't know yet. Right. Now, this looks a lot better than what we've been working with. What is the instantaneous rate of change at 2? So we've got the formula. What is my h value if I want instantaneous? 0. And what do you see? 64. Isn't that beautiful? Okay. Remember, we're trying to get h to 0. We couldn't put h to 0 because h was in the denominator. So we plugged in the IROC formula and put a 2 in for t, right? Because we want it when t is 2. Expanded and simplified and got it down. This is my equation. And now if I put 0 in for h, I'm left with, which actually should not surprise you because we already found that the instantaneous rate of change at 2. H can't be 0, but I canceled it out. It's actually a hole in the graph right there, right? If you cancel out top and bottom with a variable, it creates a hole there. But algebraically, if I cancel it here and then I plug in, it allows me to do that. We're going to do a lot of that kind of stuff when we get to derivatives. You can. What? I love that. All right. Before I show you before we relate this to limits, I am going to give you a 30-second brain break to let all this sink in. 2 minutes, always. Okay, yeah. Most of you have already made the connection that what we are getting, we're doing all this in preparation to show you limits. Yes. So, if I look back at that example, would you agree that the limit as what? You can't go to 0. So I'm trying to find, as h gets closer and closer to 0, I'm trying to find what that value would be, right? Are we all okay with that? As h goes to 0. Right. So let me show you how we write a limit. And you should know this, but if you don't, it is a little arrow. So I say the limit, and then under it, no, x approaches some value. It doesn't have to be 0. It could be infinity. It could be a value. It could be whatever you want. So this is saying the limit. So it's saying as x gets closer and closer to the c value, and then I have some equation, some function, right? In this case, what was the function? Right. 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 And so it equals. So this is the limit, just some value. The limit as x approaches, and again, I hope you know this, as x approaches c of f of x is L. A constant, a value. For right now, it's a value. Yeah, that's the word form. That's how you read it. How you write it and how you read it. Now, I want you to take out your calculator for a minute. Uh-oh.
Give me my calculator back. Wait, what is that?
Any number is just a value. And I want you, by the way, while Dylan finds his thing, what is the limit as h approaches 0 of 64 plus 16h? You should know this. We just did it. 64. The limit as h approaches 0 of 64 plus 16h is 64. That's what we just did, right? The closer h gets to 0, it approached that number. This is just the manipulated form. So at 2 seconds, it was 64 feet per second. Okay. Just so you see how that's written and how we do that. And notice, essentially what we did was just plugged in, right? The limit as it goes to 0. So as it gets closer. So a lot of times to find a limit, we can just plug the value in. If you can ever plug the value in, plug the value in. Okay? But you can't, whenever we run into problems, that's whenever we have to start getting closer and closer and closer. And so let me show you this example. I want you to grab, how did you know what I was going to do? This is a very important example, and whenever we finish, you'll want to highlight this little tidbit in your notes. If I have f of x equals sine x over x, and I said, okay, guys, what do you think? First of all, I want you to graph it, and I want you to look at it and see what it looks like.
I don't have a graph there.
How do we know what the time is? That's what you mean, its own graph.
Yeah, we're graphing it. I'm going to have to go to Desmos because I still don't have my thing hooked up here. We won't be using Desmos in here. What? Mm-hmm. So it was giving you the answers? Sine x over x.
Wait, so you were just asking us to use our calculator?
Yeah, just use it to graph. And I want you to look at this graph. Right?
That's a graph if I've ever
Okay, but
it still repeats though.
okay, so does this have a value at 0? Why? It looks like it. X can't be 0, right? There's something going on. There's a problem because I can't have X. So as I zoom in, it even still looks like, but we know it can't be, right? Okay, so what if, so I cannot have,
does not exist.
does not exist. F of 0 does not exist. It's undefined, right? So what I have to do is I have to look at it as a limit. The limit as x approaches 0 of sine x over x. And what I want you to see here is the point itself doesn't have to be defined for it to have a limit there, okay? We can clearly see by the graph, if you had to guess what the limit was looking at this graph, What do you think it is? 1. I would guess 1 also. This is a really important limit. And you're going to see it come up so many times. So we're saying the x can't be 0 for this function, but the limit as it gets closer and closer to 0, it gets closer and closer to 1 on y.
You can just like graph these.
So as it's going,
Sometimes, yes,
as it's
as long as
going
it's
into
calculated
zero,
properly.
as it's going into 0, it's getting closer to 1.
Right. Right. Highlight this in your notes. Okay? Very, very, very important. It's one of those things that if you just know off the top of your head, it's going to help us with some of the algebraic manipulations as we start evaluating limits. Function does not have to be
Wait, what did you write down? What did you write down?
what?
No, I already wrote function does not have to be defined to be a limit. So there's a hole in that. Wait, what do you mean? Does
That means.
Right. It doesn't have to be continuous.
Oh, I remember this. Thank you. Maybe I learned more than I thought. Because it would be like, because it would, remember this, wait, this would be like, this is where they graphs and jump and
Yes,
stuff like that.
yes, yes, yes.
No, I'm doing it.
Some of them, yes.
Yeah.
All right. Let me not do that one. Let me just do a line to start with. What is the limit as x approaches 1 if all of these are 1 unit? What's the limit here as x approaches 1? This is f of x, of f of x. 1. As x goes to 1, as x goes to 1, okay, are y'all with me there? What if I change it? Yep. What is the limit? Oh. As x approaches 1 of f of x, given that the purple line is f of x. So as x gets closer and closer to 1, or as x becomes 1, what happens to y? It also becomes 1.
Oh, so that's where it lines up.
Okay. This actually has the 0.11. Remember, if we can plug into a limit, we plug into the limit, because if the function is defined there, that makes the limit easy, right? And the function is defined.
Let me
Okay, go man.
So, even though this is an arrow going this way, what she's saying is while x is going to 1, so this is x, it's moving along to the right, it's moving up this line.
He's right.
As it gets to 1, which is this value right here, so x is moving along, what is the limit of f of x of y? So what is the limit of y? So as it's moving, as x is going to 1,
As you move right, getting closer to 1,
It can't get past.
what is y doing?
It can't go past.
it's not saying that it can't go past 1. Obviously it can, but what it's
Because
saying,
I can
one
approach
is that
it this way
won't.
too.
So let's say, Ms. Lee, can I try? So let's
Yes.
say, can I write on this?
You should, it might not let you.
All right, so let's say it's right here. Let's say this is 2. As it gets to 2, which will be somewhere up here, it's going. Boom, it gets right here, you have to look at that y value, which would also probably be.
It's not saying that. It's
But
because
I'm confused how this has to do with limits. This is just like.
Right.
So as it.
Right.
Like, I just think like. What does that do? Like,
Because the limit, if you're looking at the limit as x goes to 1, your first instinct should be what is y when x is 1. Because if that has a point there, then that's the limit.
It could be.
Okay.
If the point is defined where you are looking, then that is the limit right there. Well, I shouldn't say the point is defined. If the point is defined on that function, because we're going to look at one that doesn't, you're still looking at.
It has a solid dot. That's how I would look at it.
Okay, so
But not necessarily.
not necessarily, because
Well,
what
yeah,
if it looked like this? Same line, but now I have a hole at 1. This is still 1, 1. Okay? Let's say this point is 1, 3. So my function is defined at 1. Here I'm defined, right? But that's not the limit as x goes to 1. The limit as x goes to 1 of f of x, it's not 3 this time. It's still 1. As I get closer, and it's only leaving out that 1 point, as I get closer and closer to 1 here, this value is getting closer and closer to 1. Remember, limit deals with, I'm changing the distance between so small, I'm getting as close and as close and as close and as close as I can.
Like, seriously.
Getting as close as you can to that value without maybe necessarily even being that value. So as I get as close as I can to 1, not meaning that it's necessarily 1. It might be. It might be that I can just plug 1 in. But getting as close as I can to 1, what's happening? It's getting closer and closer to what? 1. Let me show you another one. This is the graph of what? Close. Right? What is the limit as x approaches? This is a terrible first example. Don't write that one. Well, but you can't do. I wanted to show you. Let me do a tangent. Let's define this. Let's not worry about the other side of this, okay? As I get closer and closer to pi over 2, so I want this is still going to be a one-sided limit. That's a square root, but it's still not, they're going to be defined at every point. I'm trying to think of one that's not going to be defined. It's going to have.
Well, you could do one like that. You could do a sign, or maybe not a sign. One of those ones.
Let's do it like this. I can't remember the exact equation of this. Let's call it f of x. What happens here as x approaches 0?
Y approaches 0. Yes. Y is approaching 0.
Y is going to 0. See? Do you see this? Do you see how it's different? As I get closer and closer to 0, it's approaching infinity. So the limit here, as x approaches 0 of f of x, would be infinity because it's going up, 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 up. It can't actually be infinity, but it can approach infinity. Just like it can't actually be 0, x can't actually be 0 there, but it can get really close.
going towards 0, but it's also going.
Yes. There's an asymptote there, right. We just got way deeper than what I wanted to get today, but that's okay. Because I really want to give you the properties so you can do your homework. I know.
Is that a lot of work?
My middle name is actually
Not just Robin. Just ask, this isn't a problem.
Y'all are such loving children. There are 7 that I want to run through real quick. They're not hard. They're super easy and they're very intuitive. Okay. The first one is, this is not actually, I'm not even going to call it number 1. I'm just going to call it just important property. The limit of a constant is always the constant. And it makes sense if you think about it. So if I have the limit as x approaches some constant value of, and then here's my constant. All 7? Now go to a new page. Go to a new page. I don't know unless you want to double row it. Oh, then yeah, you can hold it. If that's all today's stuff. Yeah. All right, so this makes sense, right? The limit is x goes to 2. If your function's always 5, it's always going to be 5. It doesn't matter. The y value is 5 regardless. It's always defined. It always is y. It never changes. Yes? Okay. Property number 1. Sum rule.
My middle name's actually.
That was just a little extra
My middle name's actually.
freebie for you. Yeah. A 5 would be 5. The limit as x goes to a 4 of 17 is 17. It doesn't matter. It's just always going to be that constant value. Okay. Sum. You can break limits apart with addition if you start adding. So if I have the limit as x goes to c of f of x plus g of x, this tells me that I can break this apart as the limit as x goes to c of f of x plus the limit as x goes to c of g of x. You can split them up. It does. These are very, I started not even listening, just started to tell you to look at the chart in your book, but you don't have your book yet, so I will write them. I'm going to include with this number 2. If you want to write it as a separate line, you can, but it's difference, right? So if I can split them up when I'm adding, then it should make sense to you that I can also split them up if I am subtracting. So whether that's plus or minus, I can split them up, adding or subtracting. Yes. 1 and 2. So purple is number 2. Well, that was just a little freebie I gave you. It wasn't really a number. Unless you want to call it 1. Doesn't matter. I just threw that in there because some students they didn't understand that last year.
So basically,
if I had the limit as x goes to 3 of x squared plus 3x, okay, then I could split this up as the limit as x goes to 3 of x squared plus the limit as x goes to 3 of 3x. That way, and then I could evaluate. What's the limit as x goes to 3 of x squared? But plug the number in, right? Because think about, that's a parabola, right? If I go to where x is 3, what's the y value there? It's 9. There's nothing that's causing me to be undefined there. I don't have to worry about any of that. It is a straight quadratic parent graph there, right? How about 3x? What's the limit as x goes to 3? 9. So the limit as x goes to 3 of x squared plus 3x is 18. 18. You can ever plug in, we're just going to plug in if it's a defined function. The problems happen when I start dividing by 0 and have asymptotes and that kind of thing.
Can I write all that?
Yes. Oh my goodness, we're almost out of time. No, we have product quotient and constant rule. Okay, I'm going to stop there. I'm not rushing. There's no point in rushing.